Hello, everyone, and welcome to our seventh lecture of GPU computing. Today, we're going to be talking about profiling. In other words, how to profile our CUDA applications to see how well they're performing and where the bottlenecks are. So last time, we spoke about DRAM banks, and we looked at how a DRAM bank is organized. We said we have these DRAM arrays that consist of DRAM cells. And the address, the memory address is divided into a row address that accesses the DRAM array, and we read a whole row of the DRAM array. And there's this slow process of going through the sense amplifiers and putting it on the column latch. We also have to write it back because when we read it, we destroy it. So this whole process is slow. But once we have that row in the column latch, the column address is used to select which part of the row that we read we want. And this is a relatively faster process. And it turns out that if the next access that comes along has the same row address but a different column address, then we don't actually have to read the entire DRAM array again. We can simply change the column address on the mux to read a different part of the whole row that we read. And we call this a burst. This whole row that we read from the DRAM array, this is called a DRAM burst. And if our accesses land on the same DRAM, of consecutive accesses land in the same DRAM burst, then they are faster. So the timeline looks like this. If we have accesses to different DRAM bursts, then we have all this time that we have to wait to read from the DRAM array, and then we have the part where we read the part of the burst that we want. And then if the next access is to a different burst, then we have to wait again until we read the DRAM array, and then we read from the burst, the part of the burst that we want. However, if accesses land in the same burst, then we can simply read from the DRAM array, and then we read part of the burst, and then if the next access is in the same burst, then we just read the next part of the burst, and it's much faster. And because of this, what we like to do when we access global memory is we like threads that are in the same warp to access consecutive memory locations, because when threads that are in the same warp access the same memory locations, they're going to issue load instructions to that are most likely at the same time that are most likely going to hit the same DRAM burst. And what the hardware can do is that it can combine accesses combine accesses to nearby locations into a single access, such that only one DRAM transaction is needed. And this is known as memory coalescing. On the other hand, if threads in the same warp at the same time access memory locations that are far away from each other, then these accesses cannot be combined, and each access will require its own load operation, and the row warp will have to wait for all the load operations to complete, and this is known as memory divergence. We also saw how we usually have multiple DRAM banks. You can't have gigabytes of DRAM all in one DRAM array, so we usually have multiple DRAM banks, and we read from one of these banks at any point in time. What this does is that it gives us a way to hide the DRAM latency. So if I'm reading from multiple DRAM banks, then while I'm waiting for one of the DRAM array for one of the banks, I can be reading from the burst of the other bank. And then by the time I finish reading these bursts, then maybe the other bank is ready. I can read those bursts. And by that time, maybe there's a third DRAM bank that I was reading from the DRAM array, and now it's ready, and I can read those bursts. And by the time I'm done, I go back, and then the other DRAM bank is also ready for me to read its burst. So for me to effectively utilize my DRAM, I want to have many memory accesses at the same time going to different banks in order for me to hide the latency of the different banks, so that I always have data in my memory system ready for me to consume. So we saw how having high occupancy in our SMs not only helps us hide the latency in the cores, but it also helps us hide the latency in accessing our memory. We then looked at another optimization, which is thread coarsening. And we said that thread coarsening is an optimization where so far we've been assigning threads to the smallest possible unit of parallelism, but we saw how the thread coarsening in the thread coarsening optimization, we have a thread process more than one unit of parallelism, and what this does is that it allows us to eliminate any redundant work across threads or any price that we pay for parallelism. And an example we gave is with tile matrix multiplication. We saw how different thread blocks that are processing different output tiles might be loading the same input tile. So here the thread block assigned to the dark orange output tile and the other thread block assigned to the light orange output tile both read the same blue input tile. Now, if these two thread blocks are going to be running in parallel, then fine, this redundancy is a price that we pay in order for us to get parallelism. However, if these two thread blocks are actually going to get serialized by the hardware because I have many more thread blocks than the hardware can simultaneously run, then maybe it's better for me to just have one thread block be responsible for these two output tiles and have this thread block read this input tile and the green input tile and then compute this output. And then before proceeding to the next tile of A, it simply keeps the same tile of A and goes to another tile of B and processes a different output tile. And by doing this, what we've done is we've saved having to load this tile of A redundantly for both this output tile and this output. And with that, this was a summary of the different optimizations that we've covered so far. Tuning resource usage to minimize occupancy, minimizing control divergence to get SIMD efficiency, having a uniform memory access pattern so that we have memory coalescing, using shared memory tiling to capture data reuse, and then thread coarsening to basically eliminate the price of parallelism. That price of parallelism could be redundant data that we load, it could be redundant operations that we perform, or it could be something else like synchronization overhead that we will look at an example of later on. And with that, we said that there exists a tension between these different optimizations. For example, when I maximize occupancy, what I might end up doing is I might end up, if I have the maximum amount of occupancy, the maximum number of threads on my SM that I can possibly have, if these threads access a lot of data, these threads may end up starting to compete for the cache, for example, and they start evicting each other's data out. And sometimes that's fine. And sometimes it's worth it for us to thrash our cache in order for us to maximize occupancy so that we can hide our latency. But at other times, it might be the case that no, I prefer for my threads to, I prefer to, for me not to have too many threads, so not to operate at maximum occupancy, in order for me to have better cache behavior. So this is an example of where having too much maximizing occupancy might actually hurt performance. Another example is shared memory tiling. So when I use shared memory tiling, every thread block needs to reserve a certain amount of shared memory. And if I use more shared memory, that allows me to have more data reuse. However, if I use too much shared memory, I could end up in a situation where my occupancy is limited. Because, for example, if my SM can take 2048 threads, so I create thread blocks that are 1024, that means my SM can take 2 thread blocks. However, if one thread block requests the maximum amount of shared memory on the SM, then because of the shared memory requirement, the SM will only be able to have 1 thread block or 1024 threads running at the same time, even though theoretically it can have 2048. But the shared memory request limits my occupancy. So this is another example of where there's a tension between these different optimizations. And we also saw how thread coarsening, when we have coarsening, it reduces our redundant work. But threads, when we coarsen, every thread may require more resources, which again may limit our occupancy. And based on this observation of there being a tension between the different optimizations, what we said is that we need to find a sweet spot that achieves the best compromise between competing optimizations. And an important part of finding that sweet spot is understanding what is actually limiting the performance of my kernel, right? Is it the memory, or is it divergence, or is it, is it something else? To understand what is limited, so basically you need to know your bottleneck. So a bottleneck is basically a constraint that limits the performance of an application, right? There's all kinds of different resources that we reuse when we execute on a piece of hardware, and one of these resources runs out before the other. Okay, so I may run out of bandwidth before I run out of flops, or maybe I run out of flops before running out of bandwidth, or maybe I run out of thread slots before I run out of shared memory, or maybe I run out of shared memory before I run out of thread slots. So there's all kinds of different resources that may limit my performance, and the resource that limits the performance is called the bottleneck. And when we this bottleneck, it depends on the application, right? Because different applications use different amounts of resources. So the bottleneck is going to depend on the application. It also depends on the device, because different devices also have different amount of resources. Some devices have higher memory bandwidth than other devices. So the combination of the application and the device it dictates what the bottleneck is. And the optimizations that we've seen so far often trade off one resource for another. Okay, so usually when I apply an optimization, I use more of one resource in order for me to use less of another resource. So for example, when I apply shared memory tiling, I use more shared memory in order for me to use less of my global memory bandwidth. So knowing but for example, if my application is not limited by global memory bandwidth, it's limited by occupancy because of shared memory, then obviously a solution to my problem wouldn't be to use more shared memory. A solution to my problem, or a solution for me to optimize performance further, is maybe to reduce the amount of shared memory. So this just highlights the importance of knowing what your bottleneck is before going and applying an optimization, because you don't want to apply an optimization that trades off the resource that is actually the resource that is bottlenecking your performance. Okay, so it's important for you to be able to properly diagnose what is the bottleneck of your application so that you don't optimize for the wrong resource. Okay, any questions about what we covered last time? I know last time I kind of rushed the end because we ran out of time. I think we also had some connection issues last time, and that's why we ran out of time. So does anybody have any questions about what we covered last time before I move on? Okay. If there are no questions, then today what we'll be talking about is how to know your bottleneck. Okay. So today we'll be talking about how to know your bottlenecks, and the answer is through profiling. So the CUDA platform provides a profiler that allows you to profile your application, see what's limiting your performance, and analyze your bottlenecks in order for you to decide what is the best optimization to apply. So we'll be doing kind of an example of profiling today, and we'll be referring to the Vector Addition application that we implemented, in the second lecture of the course, so way back in the beginning of the course. Okay, so let me switch to the terminal. Over here, I have my vector add kernel that we implemented last time. Let's take a look at it. So here, if you remember, this was Vector Addition kernel. There was basically a thread that was reading two output elements and writing to an input element. Okay, there's two things that I changed in this file. The first thing I changed is I added this header file over here, CUDA Profiler API. And at the end, what I did, so at the end of the main function, I added this call to CUDA Profiler stop. Basically, what this does is if you're profiling your code, it just makes sure that before the application exits, all the profiling information that was collected would be kind of saved before the application exits. So this is why I added this call. Okay. Everything else is the same. We call vec-add on the GPU. Here we do our CUDA mem copy. We call our kernel, and then we do CUDA mem copy back, and we do CUDA free, and then the kernel is also the same. So let's get started. I'm gonna compile this. Okay, and before we just run the vector addition, and it runs, and then we had inserted certain commands in our code to print out the timing information. Okay. Well, it turns out we didn't have to do that because we could have actually let the profiler do it for us. And here's how to do that. So the profiler that comes with the CUDA SDK is called NVProf. Okay. So NVProf, the way you use it is there's different ways of using it. The simplest way is to write NVProf and you provide your program, your binary. Okay. So I run NVProf and I run my binary. Oops. So I run NVProf and I run my binary. Okay, it runs. And after it finishes running, what it does is that it outputs all this information for me. So this is a table, and the table basically has the different calls that we made. Okay, so here it's the time that we spent copying from device to host. Here, this is the time we spent doing a memcopy from host to device. This is my actual VecAd kernel. This is the CUDA memcopy API call. Notice here it separates things into GPU activities and then API calls. These are API calls that we call from the CPU, and these are things that happen on the GPU. So we call CUDA memcopy on the CPU, and then CUDA memcopy on the CPU performs a GPU activity, which is copying from the device to host or from the host to device. Okay. So what this is telling us is that for each of these activities, so the VecAd kernel, the memcopy, the device synchronize, CUDA free, CUDA malloc, all these different things that we do, a lot of these things are happening without you knowing that they're happening because they happen under the hood. What it tells you is for each of these things, what is the time that it takes? Okay. It also tells you for some of these things how many times they're called. Okay. So here it has the time that it takes. If they're called multiple times, there's an average, there's a minimum, there's a maximum. This tells you the total time that something takes. And it also tells you what percentage of the total execution time it's taking. And what you'll notice is that the times are actually very similar to the times that we timed up here. So here you can tell that copying from the device to the host, it's telling us it takes 382.82 milliseconds. Up here, we timed it as 384.2 milliseconds. The reason is that over here, we're using a CPU timer. So here, there's a little bit of additional things that the CPU is doing while it's timing. This is probably a more precise timing for how much time we're spending copying from device to host. Okay, and it also tells you what percentage of the total application time is spent doing this. We spent 52% of our time copying from device to host. Okay, 328 for copying from host to device. Also similar here, we had 329. Our kernel execution took 13 milliseconds. It's 1.8% of the total time, and that's also similar to what we found over here. Notice that they're always slightly less because this measures a little bit more than just the pure time it takes to take on the GPU, because there's a little bit of overhead from the timers that I'm using, the CPU timers that I'm using. Okay, so this is very convenient because when you write the CUDA application, if you don't feel like inserting all this code, you saw how there's a lot of code dedicated to just be inserting timers. And the reason I did that is because I didn't want to have to run the profiler every time we do a demo in class. But if you don't want to, in your CUDA application, have to insert all these timers everywhere, you don't have to. It's as easy as just calling NVProf with your application, and it basically tells you how long everything is taking. Somebody's asking, how would NVProf work on the other machine that you guys are using, which requires you to submit jobs in batches? Well, what you could do is you could submit a job interactively if you would like to run NVProf with your application. Okay, and then we're also going to see today how we can use NVProf to also export more information about our code in order for us to analyze it using a visual profiler, and we're actually going to do that next. Okay. So this is the command to run nvprof on vector addition. This is an example of the output that we get. These timings are a little bit different from the timings I'm showing you because I obtained them on a different machine than the one I'm using for this lecture. But the trend should be similar. Okay. Don't worry about taking notes. All the commands that I'm going to write in the command line, I will have in the slides for you. So you can just sit back and enjoy the lecture, and the commands will be in the slides, so you don't have to worry about taking notes of the command. Did somebody have a question?
Yes, I wanted to ask about what's happening under the hood with the profiler. Is it like hardware counters?
So it depends what you're profiling. Over here, you're just finding the execution time of every call that the GPU does. So this doesn't really need hardware counters. You have this notion of a stream, and we will talk about streams later on in the course, but you have this notion of a stream that has these tasks taking place and they wait for each other. So inside of these streams, what nvprof does is that it simply times how long each activity takes. Okay, so it's quite easy for you to imagine, that when you call quitmcopy, inside of quitmcopy, when it starts and when it finishes, there's the runtime system is somehow taking care of starting a timer when you start and then stopping a timer when you stop. Later on, what we'll see is we're actually going to profile all kinds of things like the cache and occupancy and memory bandwidth and all these things, and these definitely use hardware counters, and you'll actually see kind of something going on that shows you that these hardware counters are being used. Okay.
Okay, thank you.
Let's do that. We're just about to do that. So let's say I wanted, so here it prints these timing results for me at standard output, but let's say I wanted to export these values to a file so that I can analyze them more visually using a visual profiler. Well, I can do that, and the way to do that is like this. So before, what we did is we called nvprof on our vector add executable. If we want to export these timing results to some file, we can actually write -o and provide the name of the timeline file that we want. So here we can write something like timeline.prof. You don't have to say .prof. You can name it anything you want. I just like to call it .prof to remind myself that this is a file that contains profiling information. Okay. So here I can run nvprof and provide it with and tell it that I want it to export all this information to a profiling file, and it does that for me. So here I'm going to run it again, and it runs, and it's going to export the information. Okay. Okay, and you see it tells us here that it generated a result file, and that this result file is at this location. All right. Now, what this does is it gives me timing information. But if I want other kinds of information related to things like occupancy, things like instruction count, things like memory bandwidth, I can actually also generate that information. And to do that, there's a command which if I don't want the timing information, I want other kinds of profiling metrics, I can actually write -m, and I can specify what are the profiling metrics that I want. Here I'm just going to write all because I wanted to export all the profiling metrics. But you don't have to write all. What you can do is you can look at the documentation, see what profiling metrics are available, and you can maybe you're interested in a specific profiling metric, and you can just export that. Okay, and now what it's going to do when I write -m all is that it's going to output not the timeline, not these timing results, but it's going to output these profiling metrics to the profiling file. Now I don't want to overwrite my timeline.prof file, so I'm going to call this something else. For example, I can just call it something like metrics.prof. Okay. Now you'll notice that when I run this, these profiling metrics that we're about to collect, about things like occupancy, cache, memory bandwidth, things like that, they use hardware counters. And obviously there is an overhead to using hardware counters, because when you start profiling, you're interfering with the execution of the actual kernel, because profiling takes time. You're spending more time gathering all these statistics about the cache, all these statistics about occupancy and things like that. So because we don't want to interfere too much with the performance of our application as we profile it, because then our profiling is not going to be accurate. What MVProf is going to do is that it's actually going to run our kernel multiple times, and each time it's going to collect a different set of profiling metrics. You're going to see that happening right now. So when I run this, it says MVProf is profiling, right? And then so here it says notice it says replaying kernel, replaying kernel, replaying kernel, and every time it collected a different statistic. Okay, notice how the overall time took longer. The reason is that this is actually running many kernels, not just one. So the timing information we're getting here is not reliable, but the profiling information that we get is hopefully reliable, because we ran a kernel many times, and each time we collected a different set of profiling information. Okay, so now we have our profiling, our timeline in timeline.prof, and our metrics in metrics.prof. Now what we would like to do is we would like to take a look at timeline.prof and metrics.prof and see what information they give to us. And the best way to do that is using the NVIDIA Visual Profiler. There's also something called Nsight that comes with different IDEs. So if you're using Visual Studio or Eclipse, you can use something called Nsight. That's also a very powerful profiling tool. But for simplicity here, I'm just going to be using the NVIDIA Visual Profiler. And to run that, I'm going to run NVVP. So NVVP, now the NVIDIA Visual Profiler uses a graphical user interface. And since this is a command line, it doesn't display graphical user interfaces. I'm connected to a remote machine via command line here. So what I've done is when I connected to this machine, I actually enabled something called X forwarding that allows you to forward the graphical user interface that's running remotely on this machine to be displayed on your local machine. So here NVVP is actually running on the server, but it's going to send me the graphical user interface so that I can display it on my computer in which I am using to teach the lecture. Okay, so I'm going to run NVVP. Okay, I'm going to put this at the end so that I can keep using the command line. This tells it to run it in the background so that it doesn't. So that I can keep using my command line after I run it. Okay, so I ran NVVP. It takes a while to run. It's sending me the graphical user interface. Here it tells me to specify where I want to put the temporary files that the profiler is using. I just press OK. And now it's launched the profiler, and this is what the profiler looks like. So here you can create a new session, and this you can create a profiling session where you can use the visual profiler itself to profile the application, or you can import profiling files that you generated using NVProf, which is what we did. So what I'm going to do is I'm going to hit import, and I'm going to specify that I'm importing files that were generated by NVProf. I hit next. You can profile multiple processes. We just have a single process. I'm just going to keep it a single process and hit next. And then here it asks me for the timeline file and also asks me for the metric file. So I'm going to browse to find the timeline file. Here my timeline file is over here, timeline.prof. And then I'm going to browse to find the metrics file, and here the metrics file is metrics.prof. Okay, then I'm going to hit finish. And what this does is that, let me maximize this. So now what it has done is it has it put the timeline over here, and then the metrics we can take a look at down here. So let's take a look first at the timeline. So here what the profiler does is that it has this timeline. Notice up here you have seconds, and over here on the left you have the different activities that take place. So we have things like memcopy, host to device, things like memcopy device to host, things like compute. So here we have the VECAD kernel that we executed. And then you also have something like streams. So everything we'll look at streams later, but basically everything we're doing now is going into the default streams. You will see all of these things overlaid with each other in the default stream. So over here, this is the CUDA device synchronize I executed at the very beginning. And then here you don't see anything over here because this is the time that the CPU was spending generating the data. And then later on, once the CPU is done generating the data, over here we can see our actual timeline. So you'll see what's happening here is that you'll see the time that is spent doing CUDA memcopy. Okay, so it tells us it's doing CUDA memcopy here. And then there's also a little bit of time over here, if you can see it. This is the time that it's done. It's using CUDA malloc. Okay, and then here you do CUDA memcopy. And then over here, you're doing another CUDA memcopy. Here, remember, we copied 2 arrays, not just 1 array. And then over here, this is the time it took for the vector addition kernel to execute. Okay, so let me, if you guys, so here, notice how here it says CUDA memcopy. So this hosted device. This is CUDA memcopy device to host, so that corresponds to this. This over here is the vector addition kernel, so that corresponds to this. And then this here shows you the stream where everything's overlaid. So you'll see what the time it's taking. So here it tells you it spent this much time doing CUDA memcopy hosted device, and then this much time doing another CUDA memcopy hosted device, and this much time in the vector add kernel, and this much time doing CUDA memcopy device. And then this over here at the end is also doing the CUDA free stuff. Okay, notice down here, if you take a look at what's showing up over here, it'll show you that it says CUDA free, and it tells you the start and end time. Same thing over here, it'll show you that it's saying CUDA malloc over here. Okay. Any questions about the timeline? So this is a prettier way of visualizing where time is being spent in your application compared to this old school way of using the profiler, the NVProf, to just throw out all these numbers. And also, these are for different purposes. This is quicker over here; you just get the numbers quickly. Okay, but this is if you want to do a more in-depth analysis and spend more time on it. Any questions?
So, Doctor, but this doesn't tell us if our application is memory bound or
right. So we're going to get to that next. So this is just the timeline, and we're just about to look at the profiling. Okay. The profiling of the metrics. I just wanted to see if anybody has questions about the timeline. I think it's fairly straightforward, right? Maybe not many people have questions. Okay, so next, let's now take a look at the profiling results. I'm going to hide the timeline a little bit. And here, what we can write something like examine GPU usage. And when we write examine GPU usage, it tells us some high-level information about the overall GPU usage of our application, the whole application. And you'll notice that it tells us, oh, there's a low memcopy efficiency, there's low memcopy overlap. Basically, you can actually overlap multiple calls to memcopy. So just telling us that we're not doing that, and we are doing that because we haven't learned how to do that yet. But later on, hopefully, we'll learn how to do these kinds of things. It tells us low kernel concurrency because it says the percentage of time when 2 kernels are being executed in parallel is low. So we can actually call multiple kernels to run at the same time on the GPU, but we also haven't seen how to do that. So that's why it's telling us this. And it tells us low compute utilization, etc. Now, what we can do, our program could consist of multiple kernels. And what we can do is we can go and examine individual kernels. Now, in our case, we just had one kernel, which is the vector addition kernel. So we click on examine individual kernels. Here, there's just one kernel. But if you ran many kernels, you would see many different kernels. So when I click on this, first, it gives me some high-level information over here on the left. It tells me when the kernel started executing, when the kernel finished executing. It tells me the grid size, so the number of blocks in the kernel. It tells me the block size, the number of threads per block. It tells me the register usage, so how many threads are used how many registers are used by each thread. It tells me how much shared memory is used by each block. Okay. And here it also tells me stuff about occupancy. So it tells me how much occupancy has been achieved by the kernel. Okay. And this here tells me what is the peak occupancy that my kernel can achieve. So in my case, when I call this vector addition kernel, the number of threads per block is 512. So that's usually large enough for me to not be limited by the block size when it comes to occupancy. Also, the number of registers per thread is low. I'm not using any shared memory. So there isn't really anything that can limit my occupancy over here. And that's why my theoretical achieved occupancy is 100%. I can reach 100% occupancy in the way I've configured my kernel. The actual achieved is 88.1%. And that just has to do, you can never be 100% occupant. There's always, different things that happen that may result in you not always fully utilizing your SM. That has to do with some runtime, things that happen at runtime in the device, and just basically how things are scheduled. Okay, so now what we can do is we can go and look at more detail at this kernel. Okay, so here we can write something like perform kernel analysis. So I can click perform kernel analysis. And the first thing that I get is the utilization, and this utilization is divided into compute and memory. So it tells me how much am I utilizing my memory system and how much am I utilizing my cores. And from looking at this, does it look like this application is compute bound or is it memory bound?
Compute bound, not utilizing.
Right, so I'm not utilizing my compute. I'm fully utilizing my memory, right? So what factor is limiting? What factor is not being utilized, and what factor is limiting me from utilizing the other factor?
It's memory bound because it's using a lot more memory than compute. So
right,
it's
exactly right. You're right. It's memory bound. So remember, this is vector addition, right? So we analyzed vector addition before, and we observed that vector addition does very little operations per byte. So vector addition is memory bound, and we can see this over here because we can see that the memory system is always busy, right? It's more than 80% busy, the memory system, and that's pretty high, right? It's very hard for you to utilize the memory system 100%. Okay. Your code has to be perfect and run perfectly in order for it to utilize the memory system 100%. So 80% is actually pretty high. So your memory system is fully utilized, okay? At the compute, so the cores are actually not utilized that much, right? So I'm only utilizing my cores a little bit more than 10% of the time. What that means is that the remaining 80 to 90% of the time is the cores are not doing anything, they're idle. So that shows you that I'm really underutilizing my compute. I'm fully utilizing my memory. So obviously my kernel is memory bound. And the profiler is actually smart enough to tell me that. So if you read up here, it says kernel performance is bound by memory bandwidth. The kernel performance is bound by memory bandwidth. So a very quick way of figuring out if your kernel is memory bound or compute bound, if you don't want to sit there and count all the loads and reason about them in your code, is by profiling your code. Now, another nice thing is that over here, when it tells me how the cores are utilized, let me try it. So here, when it tells me how these cores are utilized, it actually tells me how when the cores are being utilized, how this utilization is being broken down. So what this is saying is that this dark purple is the amount of time it spends doing arithmetic operations. This teal color is the amount of time it spends doing control flow operations. And this light purple is the amount of time it spends doing memory operations, right? Because when we execute in our cores, we execute instructions. Some of these instructions perform arithmetic. Some of these instructions perform control flow, like the if statement and things like that. And some of these instructions are going to be load and store instructions. So here you can tell that most of the instructions executed by the core are memory instructions. There's a very little amount of control flow instructions, and there's also a fair amount of arithmetic operation. And this is not surprising, right? Because every thread is doing what? Every thread is doing one if statement, so it has a branch instruction. And every thread is doing two loads at a store, so it has a lot, and then it's doing one addition, and it's doing two loads at a store. So it's obvious that there's going to be more memory instructions than arithmetic instructions, and there's going to be a very little amount of control flow operation. Okay, any questions about this? We'll go into more details now, but any questions about this plot over here? Okay, so since our there's three different kinds of analyses that we can perform. There's memory bandwidth analysis, compute analysis, and also latency analysis. Since our kernel is limited by memory bandwidth, what the profiler does is that it recommends for us to use to do the memory bandwidth analysis first. It says the most likely bottleneck to performance is the kernel is memory bandwidth, so you should first perform memory bandwidth analysis to determine how it is limiting performance. And later on, if we really feel like it, we can also do compute analysis and latency analysis. Okay. So let's start with memory bandwidth analysis. When we click on memory bandwidth analysis, what the profiler tells us is it tells us how much each part of the memory system is being utilized. So here you'll notice that this table here is broken down into shared memory, L2 cache. There's something called a unified cache, and then there's also the device memory, which is the global memory, and the system memory has to do with the CPU memory. So what do you see over here? What do you notice? What part of our memory is fully utilized, and what other parts of our memory are idle?
The device memory is utilized, or the shared, or the caches are not very utilized.
Right, exactly. So here you'll notice that our device memory is fully utilized, right? Very high utilization, almost to the max. Okay. It even tells us the memory bandwidth that we're achieving. It tells us we are achieving a memory bandwidth of 124 gigabytes per second. Okay. And it also tells us that, obviously we're not using shared memory. Okay. Our L2 cache is idle most of the time. It's not fully utilized. Okay, we spend most of the time waiting on our device memory. Okay. And etc. Another thing we can see is we can see this nice image that tells us, shows us the interconnections between all the different memories, and it tells us on each of these connections what the utilization, how many requests were made. So here, this here reflects the vector addition kernel, and it tells us this is shared memory, this is texture memory, local memory, global memory, and what you can see is all the requests to shared memories, texture memory, local memory, these are all 0, and all the actual requests are to the global memory. Okay, so here this global memory, it actually tells us the number of requests, and then it shows us how go to unified cache, L2 cache, and then the device memory. It tells us how much each of these links is achieving. Okay. So this is not surprising, right? We knew that vector addition was limited by global memory bandwidth, but this kind of verifies what we expected. When you're writing very complex applications, it becomes harder and harder to reason about what's limiting your performance. So the profiling becomes even more and more important. Okay. Let's go now and take a look at compute. So obviously, if we're profiling and in order to optimize our code, it's very obvious that what's limiting our bandwidth here is what's limiting our performance is global memory. So we have to go and optimize that. But let's now take a look at what else what other kind of information we're capable of getting. So we can come back here and we can perform the compute analysis. So here, if I write perform compute analysis, it gives me different kinds of information. It tells me things about functional unit utilization. So it tells me each of the functional units in my core, how utilized are they. So there's a load store unit. There's a unit for doing single precision arithmetic, floating point arithmetic. So this is what single says. There's a unit for doing control flow, right? So this is what this says, and you'll notice that we're utilizing them all pretty low. And the reason obviously is that this is not a compute bound application. It's a bandwidth. It's bound by memory bandwidth. This over here tells us the utilization. This down here tells us the execution count. So this is the instruction count. So it tells us how many FP32 instructions we have, how many integer instructions we have, how many control flow instructions we have, how many load store instructions we have, etc. Okay, so this is what this over here tells us. And this down here tells us the types of floating point operations that we're performing. So obviously here, vector addition is only doing FP add. So it tells us that we're just performing FP add. We're not doing FP mul, for example, or FP mul add, diffuse multiply add. Okay, or any special instructions like sine and cosine and things like that. So this is nice. It tells us, what are the different instructions we're executing and how much utilization we're getting from our different functional units inside of the assembly. Okay, any questions about this?
Professor, where do the integer instructions come from?
Great question. So let's go back to our code. So over here,
Maybe it's related to memory addresses and
right, exactly.
things
So
like
this index computation is all integer arithmetic, right? This comparison here, I less than n, this is an integer operation, right? The if, the branch that branches if this condition is true is a control flow instruction, but I less than n itself is an arithmetic instruction. And then as somebody was saying, when you do z of I, what this does is this translates into several instructions that are going to calculate the address, right? Because you're going to take the address in z, and then you're gonna add I to it. But before adding I, you need to multiply by the size of the elements. So you're going to do I times 4 because the floating point number is 4. Then you're going to add it to the base address of z, and then you're going to do the store. So each one of these memory accesses involves several integer arithmetic operations to calculate the address. Okay. Clear?
Yes, thank you.
Yeah, you're welcome. Okay, so now that we've seen the compute utilization, let's also go to our latency analysis. So we can do latency analysis. And here with latency analysis, remember how we said that the most effective way of hiding latency is having high occupancy, because when we have high occupancy, we're able to hide the latency of our applications by filling in these pipelines. So here, when we do latency analysis, it tells us that occupancy is not limiting kernel performance. Okay, so you don't have to worry about occupancy. Now we already saw here on the right that our occupancy was high. But the nice thing here is that it tells us more information. So it tells us the theoretical number of blocks we can achieve per SM and the device limit. So we're under the device limit, so we're not worried. We can see that our number of active warps, our number of active threads are fully utilized, and this is what we care about, right? So ultimately, we care about having the maximum number of threads / warps executing because the threads and the warps are what hide the latency. And then here it tells us that our achieved occupancy is 88%. Our theoretical occupancy is 100%. Obviously, the device limit is 100%. So we have nothing that's limiting occupancy. It also tells us, the different resources. So things like threads per block, warps per block. None of these are kind of have reached their limit. So we're safe in terms of occupancy. Down here, it has these nice plots that help you reason about, if I change my block size, how will this affect occupancy? Or if I change my shared memory usage, how will this affect occupancy? So here it basically tells you that if you increase the threads per block, if you vary the threads per block, you get this change in occupancy. And notice how you have these intermediate values where the occupancy is lower than 100%, but then it goes back up. These are basically the situations where your total number of threads is not divisible by your threads per block. So here you would have full occupancy because of that lack of divisibility. And remember, we saw an example of this before. Okay. One final thing we can do is we can do something called PC sampling. And I think the device that I have doesn't actually support device images doesn't actually support PC sampling. However, in the slides, I've included some profiling that I've done on a different device that shows you what information you get if you do PC sampling. Let me actually switch the slides to show you that. By the way, I have a screenshot of all the different things that we saw today in the slides. If you guys would like to refer to it later on, you can also refer to the video. This is what we would get when we do the PC sampling. So what this tells us is it tells us the reasons behind the stall. Okay, so it tells us that Whenever we have latency, whenever we have stalls in our warps stalling, it tells us the reasons why these warps stall. So you'll notice that for vector addition, the most common reason for a warp to stall is what? It's memory dependency. So it's basically waiting. It's stalling because it's waiting for some memory operation to complete. And this is obvious, right? So vector addition, it's memory bound, so the kernels don't do much besides wait for memory. Okay, so here memory dependency is the most common source of stalls. Another one, for example, is execution dependency. So this is probably because of the branch that we have when we are doing the check, right? Because we have the branch that compares, that does the boundary check. So we need to wait for the branch result to get resolved. So because of this, some warps will stall until the branch gets resolved. Okay, and these are other things that are just minor things that happen here and there. And depending on what your application is, one thing or the other may be big, and that will help you reason about what's limiting your performance and what you should do. Okay, any questions about this?
Professor, why were there only 4 blocks active in, like, couldn't we have used more? Is it because the size of the array we gave it is below?
Okay, so the reason is that my block size is 512 threads. Okay, and my maximum number of threads is 2048. So 2048 divided by 512 is 4 blocks. So this is why I have 4 blocks active. But the fact that I don't have the limit, I don't reach the limit in the number of blocks is not really an issue, right? It's not an issue because what I care about to hide my latency is fully having the maximum number of warps or threads. So whether I achieve 2048 threads using 4 blocks that are 512 each, or if I achieve the maximum number of threads using 8 blocks that are 256 each, doesn't really matter. It might matter for other performance metrics, but for the sake of occupancy, it doesn't really matter if I use 4 blocks or 8 blocks that are smaller, or 16 blocks that are even smaller, right? Now, if I set my block size to 32, for example, and the maximum number of blocks I'm allowed is 32, then my occupancy will be limited because then the block size will limit me before the maximum thread count does, and that's actually exactly what I was planning to do next. So let's go.
Professor?
Yes, somebody has a question?
Yeah, I just wanted to follow up. So since the number of active blocks is the number of active threads divided by the number of threads per block, it means we have not occupied all the SMs. Like, because had we occupied all the SMs, then the blocks would have been, or can we have more than 1 block on an SM or not?
Yes. So
yes.
you can have more than 1 thread block on an SM. This information pertains to an SM, right? It doesn't mean we have many blocks. We have this many blocks up here, right? So we have enough blocks to fully occupy all the SM. What we care about when we talk about occupancy and hiding latency, we care about achieving the maximum number of threads possible.
Okay, but if like we had filled all the SMs and still there were some blocks that had not been assigned to some SMs.
Right, so those blocks are simply going to wait for their turn until other blocks finish, and then they will be assigned to the SMs.
Okay, but would we see like 8 active blocks per thread, or it would still be 4, but they would it would take longer?
This doesn't mean that only 4 blocks run on an SM for the entire execution. This means that 4 blocks at a time will run on the SM.
Okay, I see. Thank you.
Yeah, you're welcome.
Doctor?
Yes.
A significant part of the PC, like not a significant, but no, a non-negligible part of the PC sampling of the stall time was related to branches, and I don't know what was called exactly, but we have no branch prediction, not even a simple one, or speculative execution, not at all.
So how much, whether or not there's branch prediction and how sophisticated it is something that is not necessarily public information.
Oh,
Okay. However, even if there was branch prediction, it would definitely not be as complicated as that on the CPU. Okay.
definitely.
The reason being that the reason being that GPUs you care more about throughput than latency.
Throughput.
You don't care about it's fine if the branch takes a high amount of latency because you have many other warps that you can execute while waiting for the branch to get resolved.
Okay.
Okay. Yeah, you're welcome. Okay, so let's tinker with this a little bit. So let's mess with our profiler and let's see what happens if we set our thread block size to underutilize the GPU. So here, let's say, so before I had set my thread block number of threads per block to 512. Okay, now if I set my number of threads per block to 32, for example, oops. What happened? Okay, if I set my number of threads, oops, happened again. Okay, so if I set my number of threads per block to 32, for example, what we can expect here is we can expect to underutilize the GPU, right? Because if I have 32 threads per block and I have a maximum of 32 blocks allowed, that means I'm going to have a maximum of 1,024 threads that I can schedule on DSM. But DSM can support 2048. So here I'm expected to not reach full occupancy. And let's verify that. So I'm going to compile this. Okay, and I'm going to run my profiling commands again. So I'm going to profile with a timeline. Here I'm going to just write -awk to remember that this is the example where we were limiting occupancy. Okay. By the way, notice how our performance goes down, right? So before it was 13 milliseconds. Now it's almost twice as slow. Why? Because our occupancy is half what it used to be. So that's why it's twice as slow. So here, thread block size does really matter. And then we'll also generate the metrics. I'm also going to call this metrics-awk. Okay, notice how it runs many times. It replays the kernel. Okay, and now we have generated the metrics and the timeline for the occupancy. So let's go back to our profiler and let's import these new files. So maybe we'll go next. This time I'm gonna get timeline.awk -awk and then metrics-awk. I'm gonna hit finish. Okay, so now if we go and we examine GPU usage and then we examine individual kernels, we press on the kernel. Now what you notice that we have actually, I want to go back actually, sorry, I rushed this. So when I click on examine GPU usage, okay, it tells us to do the same thing. When we write examine individual kernels, we press on the kernel, okay, what you'll notice is that over here on the right, it tells us that our block size is 32. And it tells us here that our occupancy, the achieved occupancy is 35%. And it tells us that the theoretical maximum occupancy that we can achieve is 50%. Okay, so it tells us that as long if this application runs perfectly on the GPU, it won't be able to achieve more than 50% occupancy. And it tells us that the factor that's limiting our occupancy is the block size, which is what we expect. And here, if we perform kernel analysis, again, the kernel is still limited by memory bandwidth as we expect. But if we perform latency analysis, okay, now it gives us a different message up here. It says GPU utilization may be limited by block size. And notice here how the block limit is in red because the block limit now is higher than the maximum. It tells us that the theoretical blocks that we can have is 32, And now it tells us that the active threads, the theoretical maximum number of active threads we can have is 1024, even though the device limit is 2048. All right. Okay, so this this tells us, this gives us, some information about maximizing off. Okay, and notice here how it's highlighting our threads per block, and it points to 32 over here to showing us that, hey, look, you're down here. If you change your thread block size a little bit, you can come up to a higher occupant. Okay. Is this clear to everyone? Any questions about this? It's pretty neat, right? The profiler really helps with identifying what your bottlenecks are. So this here is an example of occupancy analysis. This here is an example of occupancy. Okay, and that's all. Does anybody have any final questions? Okay, well then, if you don't have any final questions, then that is all for today, and I will see you next time. Bye, everyone.